If we consider the tangent function, here's our parent function, y equals tangent x, where x is the angle and y is the vertical value. So I didn't put it in, but here's our y-axis and our x-axis. You can see that the tangent function is always increasing, meaning as x increases, y increases. And we've got asymptotes at pi over 2 plus pi n, where n is an integer, to give us all of these asymptotes. Well, clearly, if I draw a horizontal line, I'm going to fail the horizontal line test in infinite spaces. So this function, it's a function because it passes the vertical line test. It does not have an inverse function because it's not a 1x to 1y function. It's not a one-to-one function. However, I could limit the domain so that I do have a one-to-one function. And in order to choose where I limit the domain, remember, I have to incorporate all of the y values. Oh, look at this, very convenient. This goes down to infinity and up to infinity. So if I erase everything outside of from negative pi over 2 to pi over 2, meaning everything else gets wiped away here, and I say, here is my domain, and I'm going to restrict that from negative pi over 2 to pi over 2. I'm writing that in interval notation. Here is our right-hand asymptote at positive pi over 2. Notice I can't include those endpoints. They're vertical asymptotes. They're no-fly zones. So slight difference from the sine function where we had those boxy brackets. The domain here is curvy brackets. And of course, the range is from negative infinity to infinity. Well, what happens when we reflect this over this line, y equals x? So I've just drawn one cycle, one restricted domain cycle of y equals tangent x. When we reflect this over this diagonal line, y equals x, to find its inverse function, look what happens to our vertical asymptotes. Remember, this is about negative 1.57, and this is about 1.57. They become horizontal asymptotes at y equals positive pi over 2 and y equals negative pi over 2. And our curve, when reflected, is going to look like this. Now, you can see that, in fact, our y equals x line, here's y equals x. It is the reflection line, and they do meet on that line. Why was that? I went over that a little quick. Well, here is our 0, 0 point. When we switch x and y, that's going to stay the same. Here was our point. We said this was pi over 4 comma 1. Well, that is going to become, you guessed it, 1 comma pi over 4. And this point here in the blue was, remember, for the parent function, it was negative pi over 4 comma negative 1. Well, if I switch x and y, as I do when I take the inverse, this will be negative 1 comma negative pi over 4. And you can see, I'll get this nice curve. Well, the black curve is the inverse. So the inverse is y equals inverse tangent of x. All right, they are both functions. So let's talk about what we know here. We established just a moment ago that the domain here was negative infinity, the domain here was negative pi over 2 to pi over 2, and those had those curvy brackets because we couldn't include the endpoints. And the range was negative infinity to infinity. So what happens when I do the domain and range of the inverse function? Domain and range. Well, the range becomes the domain. I should have negative infinity to infinity. Let's take a look at our graph. Yep, this goes on and on forever in the negative x direction and on forever in the positive x direction. infinitely close, by the way, to this horizontal asymptote. Look what happens as x goes to infinity. The y value is heading towards pi over 2. We're going to learn about that in limits later on. And how about our range? Well, the y values go from a minimum of negative pi over 2 to a maximum of pi over 2. Notice our graph will never touch that horizontal asymptote. That's why I put these curvy brackets. Now, when we take the inverse, remember the input here is the ratio and the output is the angle. So the output is the range. Our range will be negative pi over 2 to pi over 2, or negative 90 degrees to 90 degrees, exclusive, almost like that sine function. So it's time to go from our inverse tangent function on an xy plane to the unit circle. We're talking about our output. Remember, when we're dealing with the inverse, the output is the angle. And it looks like our output goes from negative pi over 2 all the way up to pi over 2. Now, I can't include this pi over 2 and this negative pi over 2. So the way I'm going to demonstrate that horizontal asymptote, is I'm going to put open circles here. Now, I know ASTC, I'm only allowed angles in the first quadrant and the fourth quadrant. I'm not going to have them in the second and third quadrant over here. So this almost looks like the sine function, but it's got two little open circles. Remember the sine function was like Katniss Everdeen? This reminds me of Katniss Everdeen, but minus 2 arrows. Her quiver is a little light, we could say. Let's play the hits here. Inverse sine, sine with this little -1, is known as arcsine. Look at its domain from -1 to 1. That's the ratio. The output is from negative pi over 2 to pi over 2. What does that look like on the unit circle? From negative pi over 2 to pi over 2, inclusive. It's Katniss Everdeen with those 2 extra arrows. Oh, inverse cosine. Look at the graph of inverse cosine. Its domain goes from -1 to 1, just like the sine. -1 to 1. That's the input. That's the ratio. The output is the angle from 0 to pi. What does that look like on the unit circle? From 0 to pi. Domain and range for the inverse cosine. Looks like the muffin man, the top of the muffin, best part of the muffin. That's inverse cosine. And here was inverse tangent. Here's what our graph looked like. Unlimited domain. So our domain, remember, was from -infinity to infinity. That's the ratio. The output is the angle from negative pi over 2 to pi over 2. But unlike sine, I can't include my endpoints. So I have Katniss Everdeen minus 2 little arrows there. And I'm living in quadrant 1 and quadrant 4 only.